Namaste. Welcome once again to Murali's World of Physics. In this video, I propose to discuss the history of that branch of physics which is called nuclear physics. Last year, the nuclear physics community of the world celebrated the 125th anniversary of nuclear physics. It is always instructive not only to the students but also to the experts in any field of science to occasionally go through the history of the developments in that particular field over the past several decades. It will enable them to appreciate and get inspiration from the dedicated work of hundreds of scientists over those several decades to bring the level of knowledge to the current level. It is in this perspective that I have chosen the topic for today's video as 125 years journey of nuclear physics. It all started with the so-called accidental discovery of the natural phenomenon of natural radioactivity, which was discovered by Henry Becquerel in the year 1896. This particular event is often considered as the birth of the field of nuclear physics. After all, what does nuclear physics involve? A nuclear physicist focuses his attention on the study of the nucleus, which forms the central entity of all atoms, which in turn are the smallest characteristic part of any elemental material. The investigations will involve the following aspects. Firstly, the constituents of the nucleus, which we now know are the protons and the neutrons, which are collectively known as the nucleons. Then the properties of these nucleons like mass, charge, angular momentum, electromagnetic moments, etc. etc. The interactions of these nucleons inside the nucleus, that means the forces operating between these nucleons, and how they are bound inside the nucleus, how they form the bound system known as the nucleus. Then the properties of the nucleus itself, namely the mass, charge, angular momentum, electromagnetic moments, etc. And lastly, how these nuclei interact among themselves, or in other words, how these interactions lead to the processes called nuclear reactions. Investigations in nuclear physics basically involve two main aspects, just like any other science. These are the experimental aspect and the theoretical aspect. The experimental nuclear physicist tries to carry out experimental observations using the appropriate equipment, and the theoretical nuclear physicist on his part tries to analyze and explain these observations in terms of some theoretical model and utilizing several of the mathematical tools and techniques. The experimental nuclear physicist and the theoretical nuclear physicist always go hand in hand, the one complementing the other invariably. In our journey of the history of the nuclear physics during the last 125 years, we will examine the various milestones throughout these 125 years. We will start our journey with the first milestone in the year 1896. Now this event is the historic event of the discovery of natural radioactivity, which in fact can be taken as the birth event of nuclear physics itself. This was one of the most well-known accidental discoveries in the history of physics. On an overcast day in March 1896, Becquerel found that some invisible radiations were affecting the photographic plates kept near a uranium salt in a dark room. He further confirmed that these radiations were in fact emitted from the uranium salt itself. He initially believed that his rays were similar to the X-rays which were just discovered by Roentgen in the previous year. But his later experiments showed that unlike X-rays, which are neutral, his rays could be deflected by electric or magnetic fields. So here we go on our journey. We have in our car a theoretical nuclear physicist and an experimental nuclear physicist. Okay, here we go. We reach the next milestone that is the year 1898, and the event is the discovery of the new radioactive materials, radium and polonium. In 1898, Marie Curie coined the term radioactivity for the phenomenon of spontaneous emission of ionizing penetrating rays by certain atoms discovered by Becquerel. Also, Marie and Pierre Curie discovered the strongly radioactive elements polonium and radium, which occur naturally in the uranium minerals. The next milestone was the year 1899, corresponding to the discovery that the radiations from naturally radioactive materials comprise of three types. In 1899, Rutherford showed that radioactive substances emit more than one kind of radiation. It was determined also that part of the radiation is 100 times more penetrating than the rest and can pass through aluminum foil 1/50th of a millimeter thick. He named the less penetrating emanations as alpha rays and the more powerful ones beta rays after the first two letters of the Greek alphabet. He also found that beta rays were deflected by a magnetic field and concluded that they are negatively charged particles similar to cathode rays. The second part was seen to be deflected in the opposite direction and to a lesser extent. 1900, recognizing the third component of the radiations being unaffected by electromagnetic fields. In the year 1900, a third kind of radiation was identified by the French chemist Paul Villard in the radiations emitted from a radioactive source. These were designated as gamma rays, and they are not deflected by magnets and is much more penetrating than they are even the alpha particles. These rays were later shown to be a form of electromagnetic radiation similar to light or X-rays but with much shorter wavelength. Because of these shorter wavelengths, gamma rays have higher frequencies and are even more penetrating than X-rays. The important discovery of the fact that the process of radioactivity transforms the element itself was made in 1902. While studying the radioactivity of thorium, Rutherford and Frederick Soddy discovered that radioactivity was associated with changes inside the atom that transformed thorium into a different element. So this is what happens during the decay process. The original element decays via the natural radioactivity process and it gets transformed into a new element after the decay. Also, from their studies, they formulated the famous exponential decay law, which states that a fixed fraction of the element will decay in each unit of time. One can easily see that a mathematical treatment of this result will automatically lead to an equation of this form, where n is the number of radioactive atoms remaining at the end of time t, and n0 is the number which was there at the initial phase. So if you plot n as a function of time, we get the exponential decay curve. Here lambda is the decay constant. The next important milestone was 1903, when the alpha particles were identified as positively charged helium atoms. In 1903, it was Rutherford who found that alpha rays were deflected slightly in a direction opposite to that of the beta particles, thereby showing that they are more massive and also positively charged particles. Somewhat later, he also proved that these alpha rays are nuclei of helium atoms, and this was proven by collecting the rays in an evacuated tube and detecting the buildup of helium gas over several days. On the theory side, the milestone 1905 is especially important, being the epoch of the special theory of relativity developed by Dr. Albert Einstein. And associated with that, the famous mass-energy relation is equal to mc squared. Now this had very far-reaching consequences, especially with regard to nuclear binding energies, nuclear reaction energies, nuclear fission, nuclear fusion, power generation, etc. etc. Here there is a sample calculation of the binding energy of a particular nucleus, and here is shown the variation of the average binding energy per nucleon as a function of the mass number. So you can see that this is a particular shape of this curve which has a sort of maximum around nucleus iron 56. So that means iron 56 is the most stable of all nuclei. Those nuclei which lie above iron 56 tend to undergo the fission process, and those below iron 56 undergo the fusion process. In 1906, Rutherford experimentally confirmed the nature of alpha particles. He showed that alpha particles stopped in matter cause accumulation of helium gas in the material. Obviously, they become neutral helium atoms. So therefore, alpha particles are nothing but helium nuclei. The famous alpha scattering measurements were made during 1909 to 1911. During the years 1909 to 1911, the famous alpha scattering experiments were carried out by Rutherford and his group, comprising of Geiger and Marsden. The experiment was simple. They used a alpha radioactive source, and the alpha particles from this source were allowed to bombard on a thin gold foil, and they looked at the scintillations produced on a zinc sulfide screen kept at a distance from the gold foil. So this will give light flashes whenever particles bombarded on it. It was seen that some alpha particles were scattered in different directions, whereas most of them passed straight through without any deviation. This was the particular angular distribution that Rutherford and his group obtained for the number of scattered alpha particles as a function of the scattering angle. So the scattering process was maximum in the forward direction, and then it steadily decreased when the scattering angle increased. So this is a replication of the effect of the gold foil on the alpha particles. Most of them pass through, and some alphas are scattered, and some are even scattered at extreme backward angles. Now these results were contradicting the Thomson's plum pudding model of the atom, which was suggested by Thomson in the year 1900. So this model suggested that the atom consists of a ball of positive charge in which negatively charged electrons were embedded uniformly. Rutherford argued that the entire mass and charge of the atom was concentrated in a small volume at its center. So this is the atom. The entire mass and charge, positive charge, was concentrated at the center in a very tiny volume, and the electrons were going around it. Only this type of picture can account for entire angular distribution of the scattered alpha particles. From the alpha scattering experiments, the nucleus itself was born in 1911. Rutherford coined the term nucleus for the entity at the center of the atom. This is the real birth of the nuclear atom model. The existence of different isotopes of the same element was discovered in 1913. In 1913, Soddy elucidated the concept of nuclear mass, and from that, isotopes were born. He showed that certain elements might exist in forms that differ in atomic weight while being indistinguishable and inseparable chemically. That means they are the same elements, but their masses are different. He called these entities the isotopes of the same element. Now, the concept of nuclear energy levels is very much important in the entire field of nuclear physics. The very idea of nuclear energy levels arises from the observations that, unlike beta particles, the alpha particles and gamma rays emitted by nuclei during radioactive decay have discrete energies. The beta particles have continuous energies, but the other two types of radiations have discrete energies. Earlier, in 1913, Bohr had explained the existence of discrete energy levels in atoms in his atomic model. So it is quite natural that nuclei also may possess various discrete energy levels. So the explanation was that the radioactive nucleus during the decay goes to one of the excited states of the residual nucleus, or maybe to its ground state. So this leads to discrete energies of the alpha particles emitted. In fact, the notion of discrete energy levels naturally arises in any quantum mechanical theory involving particles bound inside a potential. The solution of the relevant Schrödinger equation automatically leads to the occurrence of ground state and discrete excited states. So this is a pattern of the energy levels of any quantum system. So we have a ground state, which is the lowest energy level possible, and above that we have several excited states which are discrete in nature. We next arrive at the next important milestone, that is 1915, when the concept of binding energy of the nucleus emerged. It was the American chemist William Hawkins who noted that the mass of a helium atom is in fact not exactly 4 times that of a proton. It is slightly less. So where does that mass go? He stated that the excess mass has been converted into energy via Einstein's mass energy relation E is equal to mc square. So this was a very intuitive idea put forward by Hawkins, and he suggested that this particular conversion of mass into energy is the source of nuclear energy itself. Then artificial transmutation of a nucleus was first achieved in 1919. Rutherford and his group carried out the first artificial transmutation. Of course, by now the alpha particle radiations were available for use by the scientists, and his group bombarded nitrogen with alpha particles and found traces of hydrogen and oxygen which were not there previously. So the alpha particles hitting the target nitrogen atom, a proton is ejected and a residual nucleus formed. This is actually oxygen. So this is an artificial transmutation of the element nitrogen into the element oxygen. This reminds us of the age-old alchemists who had always dreamt of converting the base metal iron into the noble metal gold. So they wanted by chemical methods to convert the base metal iron into the noble metal gold. So now we can say that their dreams have been realized practically, at least partially. Now we don't know, there may be a future time when it would be practically possible to get sizable amounts of gold from iron, considering the rate at which the technological developments have been progressing. The experimental confirmation of the existence of isotopes of elements came when Einstein made measurements using his new developed mass spectrograph. Here he could get a spectrum of the isotopes according to their masses. Intensive research in beta decay was another milestone during the years 1920 to 1927. The years 1920 to 1927 saw tremendous and pioneering research work in the field of the energy distribution of beta particles from beta decay. It was established that the energy spectrum of the beta particles was continuous in nature with a clear endpoint. So the distribution is continuous with respect to the kinetic energy of the electrons, and there is a well-defined maximum energy or the endpoint. It was at that point of time very difficult to explain the continuous nature of the energy in non-beta decay products, as well as for conservation of momentum and angular momentum in the process at the same time. So these are some of the difficulties with regard to the beta decay process which had to be explained. The concept of nuclear spin and its associated magnetism was first suggested by Wolfgang Pauli in 1924. This was a conjecture based on the fine details of the atomic spectra, which was called the hyperfine structure. This was possible from observations on the splitting of the hydrogen H-alpha line, which by that time could be measured. So this splitting was attributed to the fact that the nucleus does possess nuclear spin and an associated magnetic moment. So therefore the electron spin gets aligned with spin up or spin down in the field of the nuclear magnet, and a transition between these two levels can take place, and this is the actual splitting observed in the H-alpha line. Along the line of Dirac's concept of the electron spin, which was beautifully elucidated in his relativistic quantum theory of the electron. So this is yet another instance for the application of quantum mechanical concepts in nuclear physics. A very important development on the theory side was the milestone in 1928, namely the application of the quantum mechanical theory of potential barrier tunneling to alpha decay process. In 1928, the process of quantum tunneling was quite well known in quantum mechanics, and in fact this was first observed in 1927 by Hunt while he was calculating the ground state of the double well potential. This is an excellent example for application of quantum mechanical principles in nuclear physics. The first application was in 1928 again. This was a mathematical explanation for alpha decay process by George Gamow. This is the quantum mechanical theory of alpha decay. So the decay process was explained as being due to the penetration of the Coulomb barrier by the alpha particles from inside the nucleus. So this process helps them to come out of the potential barrier, and in fact these are the alpha particles which are observed from the decay of the radioactive nucleus. A relationship was derived between the half-life of the radioactive nucleus and the energy of emission that depended directly on the mathematical probability of tunneling. So this is the famous Geiger-Nutall law. This is the probability versus the Q value of the process. The next important milestone worth mentioning is the year 1929-30, from which developments in particle accelerators progressed at a fast pace. From 1929 onwards, we have a new phase starting, namely the development of particle accelerators. Now, in the early days of experimental studies in nuclear physics, only radioactive sources were available as source of radiations for studying the nuclei. So we have the alphas, betas and the gamma rays coming out of the radioactive nuclei. These suffer from the following obvious disadvantages. First of all, as I have just mentioned, the type of radiations are limited to alphas, betas and gamma, discrete. Also, the energy of these particles are limited to less than about 8 MeV in the case of alphas and gammas, and around 3 MeV for the beta particles. Also, except for the beta particles, the other two radiations have discrete energies. Their energies cannot be varied continuously. Also, as far as the intensities of these radiations are considered, these are limited to less than about 10⁷ per second. Simple calculations will show that in order to get useful number of events in a nuclear reaction, we need typical intensities of the order of 10⁻11 or 10⁻12 per second. So obviously, the naturally occurring radioactive sources have only limited usage. As more and more experimental investigations were undertaken, the requirements became more vast and demanding. In fact, ideally, we require a source which can provide any energetic particle, electrons, neutrons, protons, alphas, lithium, beryllium, etc. up to uranium with any required variable energy and with any desired intensity. This was the reason why particle accelerators were developed. Now, what are these particle accelerators? They do the job of accelerating charged particles to the required energy, and they also provide the required variable intensity of this particle. Well, of course, these particles are charged, and therefore the most straightforward and simple method of acceleration would be by subjecting these charged particles to an electric field. So in a particular electric field with intensity E, any charged particle with charge Q will undergo a force F. So any particle with a charge Q under the influence of an electric field of intensity E will experience a force given by F is equal to Q into E, and thereby they will gain an energy equal to Q into the potential. So therefore, what do? We start with positively charged particles at high voltage, and naturally their tendency will be to fall to the ground, towards the ground potential, and during this process they will get accelerated, and the energy acquired is given by charge times the potential. So this is a simple method for acceleration. We have a high voltage terminal. The ions having charge Q are located in the high voltage terminal, and they will experience a force towards the ground potential, and they get accelerated and get an energy equal to Q into V. This principle was practically utilized by Cockcroft and Walton in the year 1928 when they designed an 800 kV generator encouraged by Rutherford. The required high voltage to accelerate the protons was generated using the voltage multiplier principle. So we have an AC voltage source, then we use a transformer to boost up the voltage to any required level, and then we use a voltage multiplier. So by increasing the number of stages, one can actually increase the output voltage. So this is these physicists standing in front of the first Cockcroft-Walton accelerator. Now this Cockcroft-Walton accelerator was then used in the first nuclear reaction experiment in 1932. So the protons accelerated by the Cockcroft-Walton machine were used to bombard a lithium target. Walton noticed that alpha particles were being emitted when lithium was bombarded using the protons. So in fact, the lithium broke into two helium nuclei. Then followed the hectic years when newer and better accelerator facilities were developed, pushing up the particle energies and the fluxes, as well as the type of ions that could be accelerated. Next in line was the Van de Graaff accelerator by Van de Graaff. So here we have a high voltage dome to which positive charges were continuously supplied from a power supply via an insulating belt which ran over two pulleys. So charge is being continuously transferred from the power supply to the dome. Then an ion source will be located inside the dome, and they will provide positive ions which will be accelerated towards the ground potential, and from that we can extract an accelerated charged particle beam. Voltages to accelerate charged particles was suggested by Rolf Woodrow in the year 1939, and it was put into practical use in the same year. So we have an RF voltage supply, and we have a set of beam pipes which have increasing length as we go from the ion source to the exit of the accelerator. Alternate pipes were connected to the positive terminal of the power supply, and the other set of pipes were connected to the negative terminal. And the electric field across a gap will alternate between one direction and the other, and any charged particle which reaches the gap will get accelerated from the previous pipe to the next pipe, and thereby gain energy. So they will have more velocity when they reach the next pipe, and therefore if they want to keep pace with the RF, they have to travel a longer distance, so that by the time they reach the next gap, the polarity of the field would have reversed, and so once again they will receive an acceleration. So in this way, the ions are continuously accelerated, and they can reach high voltages. Now this is a aerial view of the longest linear accelerator, that is the SLAC, Stanford Linear Accelerator, which has a total length of about 2 miles. This is an inside view of the accelerator system. Now, one disadvantage of the LINAC is the unwieldy length of the accelerator, because as the energy of the particles go up, the corresponding beam pipes have to be longer and longer. So the idea was put forward by Coxey and Lawrence. Why not have the trajectories of the accelerator particles why don't we bend these into circular trajectories, and then the total size of the accelerator could be reduced without sacrificing the total length of the trajectories. The length of the trajectories can be larger because they are contained within this the finite volume of the axle. So what we do, we apply a magnetic field, and then we have a vacuum chamber. These are actually called Ds. There are two Ds, metallic Ds, to which the positive or negative voltages will be applied, and we have an RF supply. So as the ions cross the gap between the two Ds, they will get accelerated. So the requirement is that by the time, now after acceleration, they will travel inside with the constant velocity, and because of the existence of the magnetic field, they will get bent into a semicircular trajectory. And by the time they reach the other gap on the other side, the polarity of the field would have reversed, and therefore once again they get acceleration. So in this way, and once they are accelerated, they will go in a circle of larger radius. So therefore they successively go into bigger and bigger circles. In fact, the trajectory will be spiral, and finally they will be extracted at the periphery of the accelerator. Now this is the first cyclotron which was built by Coxey and Lawrence. Later on, many new types of accelerators were devised as and when the need arose. Due to some reason, the cyclotron was not very good for electrons because of radiation losses, and therefore a new accelerator was devised for especially the electrons. This was the betatron in the year 1940 and was developed by Donald Kirst. A modified version of the betatron was made available in 1946, namely the electron synchrotron by Wechsler and Macmillan. A similar machine was devised for protons by Oliphant in the year 1952. In the experiment so far, a fixed target was used. Here, the target which contains the nuclei of interest is fixed, and the projectiles are moving and hitting the target with a certain velocity and energy. The new idea was to have what is known as a colliding beams. Now here, instead of the target being at rest, it is also in the form of an accelerated beam of charged particles. So therefore, we have two beams of accelerated charged particles coming one against the other and bombarding against each other. So here, the fixed target experiments consist of a narrow beam of accelerated particles directed against a fixed target composed of a large number of nuclei. The probability of hitting a nucleus is large because there are plenty of nuclei of interest. But the collision energy is relatively smaller because of the center of mass motion. In the case of colliding beams, we have two microscopic beams of accelerated particles directed against each other, and we look forward to head-on collisions. Of course, the probability will be small. So the flux in each beam should be much higher than that in fixed target experiments. But the advantage is that the collision energy would be much larger. The largest of such colliding accelerators existing in the world is the Large Hadron Collider LHC at CERN. Now this is an aerial view of the accelerator complex at CERN. The total circumference of the accelerator complex through which the beams orbit is around 27 kilometers. Now this is an inside view of the accelerator. Here the energy of the individual beams is 7 TeV, and therefore the net energy of collision would be 14 TeV. The most important discovery made with the Large Hadron Collider was the discovery of the Higgs boson, the quantum of mass, in the year 2012. Now there is a plan for constructing an even bigger accelerator, which is known as the Future Circular Collider, where the energy is expected to be pushed to about 100 TeV from the 14 TeV for the Large Hadron Collider. So the expected circumference is around 100 kilometers compared to 27 kilometers for the LHC. Let us hope that it becomes a reality in the not far away future, and very fruitful experiments be done using this future accelerator. Now, any particle accelerator will require contributions from various other technologies for its efficient installation and working. Now, some of these are the following. The actual acceleration process will require highly stable DC and RF high voltage sources with optional high current capabilities. The entire trajectories of the ions through the accelerator and following components have to be under very good vacuum conditions. Hence, the involvement of vacuum technology is very much essential. The focusing and bending of the accelerated ion beams as well as the nuclear reaction products requires stable intense magnetic fields in the form of dipoles, quadrupoles, etc. Then, technological developments in superconductivity have given tremendous boost to the use of superconducting magnets for steering the ion beams as well as superconducting RF cavities for accelerating them. Then the superconductors used for the above purposes as well as many vacuum systems require extremely low temperatures, wherein cryogenic technology extends a helping hand. Very useful developments in the above technological fields have been progressing at a steady pace concurrent with the development of accelerators. The first nuclear reaction using beams from an accelerator was carried out in the year 1932. Nuclear reactions, as we all know, are changes in the identity or characteristics of an atomic nucleus induced by bombarding it with an energetic particle. These are very important for unraveling the mysteries of the nucleus. The first nuclear reaction was carried out in 1919, performed, of course, by Rutherford group. They bombarded nitrogen with alpha particles and identified the ejected lighter particles as hydrogen nuclei or protons, and the product nuclei as a rare isotope of oxygen. In the first nuclear reaction produced by artificially accelerated particles in 1932, the English physicists Cockcroft and Walton bombarded lithium with accelerated protons and thereby produced two helium nuclei or alpha particles. This I had mentioned earlier also. Development of nuclear radiation detectors was another important milestone spanning over several years from 1908. Now we come to the development of various types of nuclear radiation detectors, which are very essential for any nuclear physics experiment. In order to study the emanations from the nuclei in the form of particles or radiations, first of all, these emanations have to be detected, physically detected. Obviously, these emanations are very small in size, extremely small in size, and are not at all detected by the human sense organs. Consequently, we have to depend on some artificial devices which are called radiation detectors. Now, what do you mean by radiation detection? It's actually a process which is based on some type of interaction of the radiation with suitable materials. The interaction will depend on the type of radiation, its energy, and the detecting material. A detector consists of an active medium composed of a suitable material. A particle which is incident on the detector and entering the detector will interact with the atoms, molecules, or nuclei of the material. This type of interaction will lead either directly or indirectly through some other process to the formation of ion pairs. That means positive and negative ions. A suitably applied electric field collects these ions. The negatively charged ions, which are nothing but electrons, are collected by the anode, and the positively charged ions are collected by the cathode. This charge collection leads to the formation of an electrical signal at the output terminal of the detector. The first type of detector for nuclear radiations was the zinc sulfide, which emits visible light flashes when radiations are incident on it. This type of detector was used by Rutherford and his group in their famous experiments using radiation sources, especially the alpha scattering measurements during 1909 to 1911. Next came the gas detectors. Now, these happen to be the simplest and easiest type of detectors, and that is why they were used from the early days of nuclear physics experimentations. In 1908, it was Geiger who introduced the first successful detector for individual alpha particles. The later versions of this counter were able to count beta particles and other ionizing radiations. The GM counter, as it is often called, comprises of a metallic enclosure, cylindrical enclosure, in which a suitable gas is taken, and there is a central thin anode wire which is given positive charge, and the outer cylinder will be given negative charge. So there exists a radial electric field between the anode wire and the cathode cylinder, and any radiation which is incident on the detector surface and enters the active volume will interact and produce electrons and positive ions. In the applied electric field, these are collected by the anode and cathode, and the collection of the charge by these electrodes will lead to the generation of an electrical signal at the output. The later modifications of the Geiger counter were the ionization chamber and the proportional counter. In the ionization chamber, we have parallel plate geometry, and therefore the electric field is uniform. The electric field lines are parallel and the field is uniform. So here also the interaction of the incident particle with the gas volume will produce the positive and negative ion pairs, and these are collected by the respective electrodes, and we get an output electrical pulse. Now this is a typical ionization chamber, ion chamber, and here we have the structure of a proportional counter. Here also, just similar to the Geiger-Müller counter, we have a cylindrical outer cathode and then central anode wire. So here also the radial distribution of the electric field lines is obvious. Then came the scintillation detectors from about 1944 onwards. In fact, the first scintillator was built in 1903 by Sir William Crookes, and this was a zinc sulfide screen. These scintillations produced by the screen were visible if viewed by a microscope in a darkened room. This technique led to a number of important discoveries, but was obviously tedious. Scintillators gained additional attention in 1944 when Curran and Baker replaced the naked eye measurement with the newly developed photomultiplier tube. Now this was the birth of the modern scintillators. Now this is the internal structure of a scintillation detector coupled to the photomultiplier tube. We have the detector medium. A typical detector medium is sodium iodide, and here the incident radiations interact and produce the light flashes, which are called scintillations. These are incident on the photocathode of the photomultiplier tube and produce photoelectrons. And the a set of intermediate electrodes which are called diodes will amplify these electron signals, and finally at the output anode we have a sizable current pulse. So this is our output detector pulse. Around 1950s, the semiconductor technology had reached a stage when several types of semiconducting materials were available. And during 1950 to 70, a number of semiconductor detectors were devised utilizing these semiconducting materials. Now this is the structure of a semiconducting detector. This is quite similar to the gas ionization chamber. We have the active volume in the form of the semiconducting material, and when the radiations are incident on it, the positive and negative ion pairs are produced, and the collection of these by the respective electrodes will produce the output pulse. There are several types of semiconductor detectors which were developed and used by various experimental groups in nuclear physics. The type of detector depends on the type of radiations or particles which are to be detected. So we have the high purity germanium detector for gamma rays and X-rays, the lithium drifted germanium detector for gamma rays, and the lithium drifted silicon detector for X-rays. And again, the silicon material can be used in charged particle semiconducting detectors. And there is one class of detectors which are very thin relative to the other types of detectors. These are called delta E detector. That means the incident particle will deposit only a fraction of their incident energy, and they will just get transmitted through the detector. Side by side with developments in nuclear radiation detector technology, tremendous progress was being made in the field of nuclear electronic instrumentation also. Now, what are these nuclear electronic instrumentation? Now, the output pulses from the detector are extremely small in amplitude. Also, their shape is not very suitable for further processing. So, therefore, we need several types of nuclear electronic modules in order to amplify these signals and also to shape them properly. There are several such specialist instruments used in nuclear experiments. Of course, these have been designed by electronic engineers, but with the help of physicists. Some of the important nuclear electronic instruments are high voltage power supplies. See, we need to apply suitable voltages onto the terminals across the detector. Then we have to amplify and shape these pulses, so we need preamplifiers and amplifiers. Then many times we have to select the amplitude of these pulses, so we need what are called pulse width discriminators as well as single and multi-channel analyzers. Well, in modern times we normally deal with digital signals, so we need to convert the analog signals from the detector through these various processing modules to the corresponding digital form. So we need analog to digital converters. Then the time information has to also to be converted to a pulse height. So we need time to pulse height converter or analyzer, then constant fraction discriminator, gate and delay generator, pulse shape analyzer, etc., etc. The little neutral and very elusive neutrinos entered the nuclear scenario in 1930. In the year 1930, Pauli predicted the existence of a new particle, neutrino. This was proposed in order to explain the missing energy and angular momentum in beta decay process. He suggested that a light neutral particle is emitted during beta decay, which carries away the missing energy and angular momentum. He even coined the word neutron for the new particle, since it was a neutral particle. Now later on, after the discovery of the neutron in 1932, this term was reserved for the new neutral and massive compared to the electron particle emitted from nuclei bombarded with protons and discovered by Chadwick in the year 1932. Therefore, Pauli's particle was named as the neutrino, which literally means the little neutral one. However, the experimental discovery and confirmation of the neutrino had to wait a few years till 1956, when Cowan and Rhines performed that feat via a very clever experimental scheme. Their experimental arrangement was to bombard a tank of water with antineutrinos from a nuclear reactor. The water contained a scintillation detector material as well as cadmium chloride. Now the scheme was that the antineutrinos interact with the material and produce positrons and neutrons. Now these neutrons will interact with cadmium and produce gamma rays. The positrons, on the other hand, will annihilate and produce annihilation photons. If we can detect these gamma rays from cadmium and the annihilation photons by the scintillator inside the water, then we are sure that we have actually detected the antineutrinos. So that was how Cowan and Ryan discovered antineutrinos. Fermi's theory of beta decay was proposed in 1934. Later, in 1934, Fermi came out with his theory of beta decay. He applied quantum mechanical time-dependent perturbation theory to explain the beta decay process in terms of this so-called weak interaction, which is responsible for the actual beta decay process. So he arrived at what is known as the Fermi's golden rule. This gives the transition probability lambda in terms of the quantum mechanical matrix element for the interaction, MIF. Here I and F refers to the initial and final states of the nucleus, and rho f is the density of final states of the system. So he applied this Fermi's golden rule to the beta decay, and finally he arrived at what is called as the Fermi-Curie plot. Now here on the y-axis we have a quantity square root of n by eta w f, which is a function of z and w, where w is the beta energy and z is the atomic number, n is the number of beta particles emitted, eta is another function. So if we plot this function versus the beta energy, we get a straight line plot, and when this is extended, it will meet the x-axis at a point which actually corresponds to the endpoint energy of the continuous beta spectrum. So therefore, such a plot will not only prove the validity of the Fermi's beta decay theory, it also helps to determine the endpoint energy. The milestone 1932 needs very special mention on account of the discovery of two new particles, namely the neutrons and positrons, and the very important phenomenon of nuclear fusion. In 1932 came the discovery of the neutron, which is a inherent constituent of the nucleus. This discovery was made by Chadwick in his experiments where he bombarded a beryllium target with alpha particles from a radioactive source. He found that the interaction resulted in the emission of some unknown radiation, and in subsequent experiments he used these unknown radiations to bombard on a paraffin target, and this resulted in the emission of protons. So various considerations finally prompted him to confirm that these unknown radiations are neutral particles with mass similar to that of a proton, and obviously these came from the nucleus. So they should be a constituent of the nucleus itself. Since it was neutral, the term neutron was given to these particles. Now the nuclear structure is complete. So we have the nuclear model where the nucleus contains a certain number of protons and a certain number of neutrons. The proton number is represented by Z and the neutron number is represented by N. So Z corresponds to the positive charge on the nucleus, and the total mass number will be the sum of the number of protons and the number of neutrons. So the symbol for the nucleus would be something like this. So Z is the atomic number, N is the neutron number, and A is the mass number. So X is a general symbol for any nucleus. So we have the nucleus composed of the protons and neutrons. In 1932, a very important discovery was made by Carl Anderson. He was actually studying the tracks of cosmic ray particles in a cloud chamber. During his studies, he found that there is a particular set of tracks which correspond to a light positively charged particle with a mass more or less similar to that of an electron. So this type of particle was quite unknown up to that time, and he had found the positive electron, and this was termed the positron, which has a mass just exactly the same as that of the electron. In fact, this was the first discovery of antiparticles, and it was a confirmation of the existence of antiparticles which were predicted as per the relativistic theory of the electron due to Dirac. Nuclear fusion is an important nuclear reaction in which two light nuclei fuse together to form a heavier nucleus, releasing large amounts of energy as per Einstein's mass-energy relation. That means there is a deficit of mass in the product nucleus which appears in the form of energy. It was in the year 1920 that the British astrophysicist Eddington suggested that stars draw their energy from the fusion of hydrogen into helium. Of course, this is a two-step process. In the first step, two protons fuse together to form neutron, and a positron and a neutrino are released in the process, and a lot of energy. Two such steps take place and two neutrons are produced, and these resulting neutrons will now in turn fuse together to form helium, and that also would produce a lot of energy. With his famous 1934 experiment, Rutherford showed that the fusion of deuterium into helium will produce an enormous effect during the process. By this he means that a lot of energy was released. His student Mark Oliphant used an updated version of the equipment, firing deuterium rather than hydrogen, and discovered helium-3 and tritium as the product nuclei, showing that heavy hydrogen nuclei could also be made to react with each other. This happens to be the first direct demonstration of the fusion process in the laboratory. It was also recognized that large probability for fusion can be achieved only if the projectiles have sufficient energy to overcome the Coulomb barrier between the two fusing entities. Therefore, it would require very high temperatures so that the two fusing nuclei possess the required high energies to overcome the Coulomb barrier. So the practical fusion equipment should be able to produce very high temperatures. Beginning in the 1940s, researchers began to look for ways to initiate and control fusion reactions to produce useful energy in the lab. From the start itself, the task seemed difficult because fusion reactions require temperatures of hundreds of millions of degrees, which was too hot to be contained by any solid chamber. So what is the alternative? So instead of that, physicists sought to contain the hot plasma with magnetic fields. One way would be to use the so-called pinch effect, where electric currents moving in the same direction attract each other through their magnetic fields. So this approach was called magnetic confinement. Starting in the 1960s, after the invention of the laser, other researchers sought to heat fuels with a laser so suddenly that the plasma would not have time to escape before it was burned in the fusion reaction. So there is automatic confinement. So the plasma would be trapped by its own inertia. Therefore, this new approach was thus named as inertial confinement. So therefore, we have two important techniques for achieving fusion. One is the so-called tokamak, where an extremely hot deuteron tritium plasma would be created and it would be confined with a magnetic field. The second technique is what is known as inertial confinement, where a small pellet of the fuel would be taken and it is blasted with a powerful laser beam. So therefore, there is a sudden generation of a plasma and the fusion reaction will take place before the plasma gets time to diffuse out. The first tokamak began operation in Russia in 1958. Subsequent advances led to the construction of the tokamak fusion test reactor at Princeton Plasma Physics Laboratory and Joint Europe in Taurus in England, both of which achieved record fusion power in the 1990s. Later on, several projects of inertial fusion power plants have been proposed and started in the US, Japan and France. The most recent ambitious reactor using the fusion process being developed is the ITER, which is an acronym for the International Thermonuclear Experimental Reactor, which was first proposed in 1985 and would be located in France. In this venture, about 35 countries of the world would be participating, and that includes India also. This machine would utilize magnetic confinement, and it is expected to give an output power of about 500 megawatts. The period of a few years starting from 1934 can be rightly called the era of neutrons. During this period, Fermi proposed to carry out reactions with the newly discovered particles, namely the neutrons. He showed that nuclear transmutations occur more readily with these neutrons, especially since they are neutral particles. His group identified at least 40 new radioisotopes. He also claims to have produced the transuranic elements Z is equal to 93 and 94. 1935 saw the emergence of Yukawa's exchange theory of nuclear forces. In 1935, Yukawa came forward with his meson theory of nuclear forces. The nuclear force is explained as a force which is propagated via exchange of particles, very similar to the electromagnetic force which is exchanged via photons. The corresponding potential relevant to this particular exchange phenomenon was specified by him as U is equal to J square e raised to minus lambda r by r, where G is the coupling strength and the lambda is a constant which is related to the range of the forces. So he suggested that the nuclear force is propagated via the exchange of a new type of particles between the nucleons. The new exchange particle proposed by Yukawa, which was later called the meson, was discovered in 1947 by Powell and Occhialini. These particles are called pions and have masses around 137 MeV per c square, which corresponds to a calculated range of the nuclear forces which agree with the experimentally observed values of around 1.4 Fermis. The study of nuclear reactions was imparted a boosting up in 1936 with the introduction of the compound nucleus model by Bohr. The compound nucleus model was proposed in 1936 by the Danish physicist Niels Bohr to explain nuclear reactions as a two-stage process which comprises of the formation of a relatively long-lived intermediate compound nucleus in an excited state without any previous memory on its subsequent decay. So we have the projectile bombarding the target, and these two together fuse together and form a compound system which is called the compound nucleus, which will be in an excited state, and therefore it will subsequently decay by emitting one or two or more nucleons, maybe alpha particles, and finally it settles down into a residual nucleus. Let's see what are the important features of the compound nucleus model. There is complete thermal equilibrium inside the compound nucleus. So the excitation energy is equally shared by all the nucleons. The compound system lives for at least several times longer than the time of transit of an incident particle across the nucleus, which is typically of the order of 10 raised to minus 22 seconds. The time scale of a compound nucleus reaction is of the order of 10 raised to minus 18 seconds to 10 raised to minus 16 seconds also. The mode of decay of the compound nucleus does not depend on how the compound nucleus was formed. Or in other words, the subsequent decay of the compound nucleus after its formation is independent of the initial participants in the reaction. That means there is complete loss of information on the entrance channel from the system. Of course, this is a debatable point, and it has been proved that this is not 100% correct in many reactions. The lifetime of the intermediate compound nuclear state is related to the width of the corresponding resonance in the nuclear reaction cross-section via the uncertainty relation. So this is the cross-section as a function of the incident energy, and we get what is called the resonance curve with a certain width. So this width is related to the lifetime of the intermediate compound nucleus state. Another important nuclear model, namely the liquid drop model, was developed from 1937 onwards. The liquid drop model was first proposed by George Gamow in the year 1929. Later on, around 1935 to 37, it was properly reformulated by Wheeler and Bohr. This model was essentially based on the experimental binding energy per nucleon, which is more or less a constant as an average value. It was experimentally also observed that nuclei have nearly constant density. So they behave like a drop of uniform and incompressible liquid. Also, the forces on the nucleons on the surface are different from those inside. That means there is a definite role of surface tension, just like in the case of a liquid drop. Now, this model was successfully applied to the nuclei, and in general, it describes the overall features of the nuclei, but not the minute details. The first application of the liquid drop model was to derive what is known as the semi-empirical mass formula or the binding energy. So it gives a semi-empirical formula given here for the binding energy of any nucleus of mass number A and atomic number Z. So this contains several terms, namely the volume term, the surface term, Coulomb term, asymmetry term, pairing term, etc. This formula could help nuclear physicists to calculate the masses of many nuclei to a good amount of precision. Also, the liquid-drum model could successfully explain the fission process, the excited heavy nucleus splitting into the fission fragments and emitting 2 or 3 neutrons in the process. So this was explained as a balance between the Coulomb force and the surface tensional forces. So the liquid settles into vibrations, and in that process a neck is formed at some point of time, and when this neck develops, the nucleus fissions into 2 fragments. So the overall features of the fission process could be explained by the liquid-drum model. The discovery of the so-called magic numbers and the introduction of the nuclear shell model were the events of the year in 1948. The originator of the nuclear shell model was Mayer, who in 1948 published a body of experimental evidences for the occurrence of nuclei with 50 or 82 protons or 50, 82 and 126 neutrons to have extra stability. Earlier on, it was evidenced by calculations by Eugene Wigner that nuclei with 20 protons or neutrons also had similar stability property. Very soon, it was established that these numbers given above, in particular 2, 8, 20, 28, 50, 82 and 126, represent special stability for nuclei containing so many protons or neutrons. So these are the so-called magic numbers. So nuclei possessing magic numbers of either protons or neutrons have a special stability as compared to the neighboring isotopes. The liquid-drum model, which was prevalent at that time, was unable to explain this particular observation. Mayer and Jensen subsequently developed the nuclear shell model to account for this observation along lines similar to that of the atomic shell model, which was well known by that time. The most important point in the nuclear shell model was the spin-orbit interaction. That's a coupling between the spin of the nucleus and the orbital angular momentum. So this was introduced by Mayer herself on a suggestion by Fermi. So once this spin-orbit interaction was also introduced into a quantum mechanical description of the nucleus, there emerged a energy level structure as given here. So there are discrete energy levels, and these are designated by various quantum numbers, and the spin-orbit interaction leads to a splitting of these original levels, and there is a gap between certain neighboring levels at some locations in this scheme, and these correspond to the magic numbers. So that was a great success of the nuclear shell model. In addition, this model could explain the spin parity and the magnetic dipole moment of the ground states of many nuclei which were known at that time. Later on, because of some drawbacks of the shell model, collective models of the nuclei were introduced by Bohr, Murchison and Wheeler. Now these drawbacks particularly correspond to the observation of deformed nuclei and the occurrence of large quadrupole moments, especially in the rare earth region. Obviously, deformation of the nuclei would definitely involve quadrupole moments for the nucleus. So this could not be explained well by the normal shell model of the nuclei. One can say that the collective models are a combination of the liquid-drum model and shell models, taking the essence of both to explain the observed deformation of the nuclei as well as the observed large values of the quadrupole moments. So these models predict that there is an interaction between the outer or valence nucleons and the core nucleons, and this leads to permanent deformation of the potential. The deformation represents collective motion of the nucleons in the core and are related to the liquid-drum model. There are essentially two major types of collective motions, the vibrations, which include surface oscillations, and the rotations, the rotation of the deformed shape as a whole. In these collective motions, many nucleons collaborate in these collective rotations and vibrations. Another epoch-making discovery was that of nuclear fission in 1938. This was to have very far-reaching consequences for practical life. The most important milestone in the nuclear physics journey is in 1938, in which year the nuclear fission was discovered. Now, as you all know, this has very far-reaching consequences in the scenario of power generation and research, and the applications of neutrons, etc., etc. The process of nuclear fission was experimentally first observed by Meitner and Fish. They bombarded uranium-235 with neutrons, whereby these neutrons were easily absorbed by the uranium nucleus to get converted to the compound nucleus uranium-236, which subsequently fissioned or got fragmented into two heavy fragments with the emission of a few neutrons. They also were successful in calculating and realizing experimentally that large amounts of energy was released in the fission process. So this has a direct connection with Einstein's mass energy relation. The total sum of the neutron and the nucleus uranium was found to be more than the combined mass of the neutrons and the fission fragments. So the missing mass was converted into energy, and that appeared as kinetic energy of the reaction products. Of course, the first application of the fission process we know resulted in a big calamity for the human race. I am obviously talking about the nuclear bomb which was dropped in Japan in the year 1947 and which ended the World War II. The first controlled nuclear chain reaction was achieved in 1942. The first peaceful application of the nuclear fission process took place in 1942 when the first nuclear reactor was realized in practice. In the University of Chicago, a team of scientists led by Fermi created man's first controlled self-sustaining nuclear chain reaction. Very intensive research using radioactive ion beams was started from 1951 onwards. A more recent and important development is the use of radioactive ion beams for nuclear reaction studies. The concept of radioactive ion beams was first mentioned by Bondorf in 1966. He pointed out the rich field of information that would be opened by a future use of unstable targets and projectiles in nuclear reaction study of nuclides far from the stability line. Why RIBs? The reason is that we can study nuclei far from the stability line, which may not be accessible by using normal stable targets and projectiles. The structure and properties of these nuclei which are very far from the stability line are expected to be widely different from those of stable as well as unstable nuclei near the stability line. So therefore, many RIB facilities are being constructed worldwide in order to push the research using these radioactive ion beams. The quest for the so-called super heavy elements, that is She, began in the year 1964. Super heavy elements, or otherwise shortened to SHE, She, these are chemical elements with atomic numbers greater than 103. That means beyond the element lawrencium, which has an atomic number of 102. Now you can see that the super heavy elements occupy the region indicated by the blue columns here, starting from element 104 up to the heaviest element which has so far been detected, that means 118. Rutherfordium, the first super heavy element to be discovered, was reportedly first detected in 1964 at the Joint Institute of Nuclear Research at Dumina. The quest for super heavy elements is continuing. The heaviest element so far detected is Z is equal to 118. The accelerator centers involved in She research are Joint Institute for Nuclear Research, Dubna, Russia, GSI in Darmstadt, Germany, Riken's Radioactive Isotope Physics Laboratory in Japan, Lawrence Berkeley National Laboratory, LBNL in USA, and Oak Ridge National Laboratory, USA. Now, what is the future of nuclear physics research? Reaching the so-called island of stability, which is around Z is equal to 114 and N is equal to 184. Now N is equal to 184 is supposed to be a magic number. So there is a sort of island of nuclides which are expected to be stable. So the ultimate aim of the future nuclear physics experiments would be to reach this particular island of stability.